Good day, folks. Welcome to Bright Mind Academy, where we bring brilliance to every lesson. Now, let's move on to question 6 under May June 2022 question paper. All right, it says now to us, all right, this is Doppler effect, okay? Yes. A car moves at a constant speed of 10 meters per second towards a stationary sound sound source, okay? Very important. Now we have the speed of the of the sound. Okay, stationary sound source. Oh, okay. So this one is the sound source. This one is the listen. Okay, for give me a moment. A car moves at a constant speed of 10 meters per second towards a stationary sound source. Okay, the sound source emits. Okay, so the car is the listener. Why am I saying the car is the listener? Because this is the sound source. Okay, so now the velocity of the sound source, it is 0. Why? Because it is stationary. Okay, then this is the velocity of the listener, 10 meters per second. Now the sound source, actually no, oh yes, sorry, the sound source has a velocity of 0 because it is stationary. Okay, and the listener, it is moving towards, approaching the what, the sound source. Okay, now they say to us the sound source emits the frequency, the sound waves of frequency 880 hertz. Now the frequency of the sound, it is 880 hertz. Now this frequency will move towards the will move will or rather let me say will be detected by the listener. Okay, will be detected by the listener, and it is traveling on in air, actually in air. I get these waves of from the frequency will travel in air that has a speed of 340. Okay, I'm not saying the sound source is traveling at a speed of 340. No, the sound waves that will be propagated will be moving at a speed of 340. Okay, yes. Now, okay, this one we do not know the frequency of the listener. We do not know it. Okay. All right. Now they say a sound detector A is attached to the car. So it is a sound emitter, but it also has a sound detector. So it means I want you to take note of this. Accurate sound source will emit waves or rather frequency to the listener, to the to the car. Let me use A to the car, right? But the car will return the waves or rather the frequency also. The frequency that, okay, let me do this. The frequency that the sound emits to the car will be returned back to the to the to B. Okay, the sound source takes the, okay, let me do this. The sound source emits the waves to A, then A will return the waves to B. Okay, now in this case, when the sound takes the waves to the A, this becomes the frequency of the sound, this one becomes the frequency of the listener. Okay, okay, let me return that. But when it returns it like this, when the when A returns or emits back the frequency, this one becomes the frequency of the sound. Then this one becomes the listener. Can you see now? From the sound to A, sound source becomes the frequency of the sound. The A becomes the listener. Again, but now from A to B, A emits now. A is now the one emitting, so it becomes the sound source. Then B becomes the listener. I believe you are following. I strongly believe you are following. Okay, yes. And now another important part is that let's say this one emits a sound or frequency of 800 hertz. When it returns, since while it is approaching, the frequency it is now get. Remember, the frequency, it is a measure of how much intensity something is, right? So as it is moving, let's say when it emitted, it was at this distance, okay? But since while it is moving, let's say the car was here. Okay, so can you see it will emit back? So now, since while it is close, you will hear more. Like we use sound, it is not necessarily sound. We will hear more pitch. more loudness. Okay, so hence now the frequency here will be maybe something 1000 hertz, because now the bee will detect a higher pitch. All right, we usually say a a higher speed, which is not necessarily not higher speed, higher sound. Okay, yes. So when it is approaching, the sound becomes more intensified. It becomes more. Okay, you hear more louder sound. All right, than it is moving away. Okay, yes. So now I think I'm done. Wait, I've been talking. So state Doppler effect. Remember Doppler effect, it is the apparent change in the frequency of the sound detected rather by the listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. This one I leave it to you and your definition part. Make sure you know all your definitions, okay? I repeat, the apparent change in frequency of the sound detected by the listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. All right. Now 6.2 says, calculate the wavelength. Let me remove this. Calculate the wavelength of the sound waves emitted by the source. All right. The wavelength of the sound waves. So the sound waves. So now remember sound waves. Now remember this sound here. This sound, it is moving on in air. Okay? So it has a velocity of 340. Okay, and it is the sound waves, not the sound source. So the velocity of the sound waves emitted, actually the wavelength of this frequency, it is how much again. So we're gonna say we use this formula that says to us, remember we have this formula, a unique formula that says um, velocity, it is equal to frequency multiplied by wavelength, or lambda. Okay, now the velocity is 340. The frequency there emitted was 808 multiplied by our lambda thereof. Okay, now our lambda, it is equal to how much? When you punch that into your calculator, you get something like 0.386. Okay, 386 meters, or you can say 0.39 meters. That's fine. Okay, yes. Okay, good. Now they say calculate the frequency of the sound waves detected by A. Okay, so now A will act as a listener. Okay, because we want, it is a detector. Someone who detects is someone who listens. Okay, so a detector is a listener. We wanted the frequency, okay, of the listener. So remember our formula goes like frequency of the listener is equal to V plus or minus velocity of the listener plus V plus or minus velocity of the sound multiplied by S, like that. Remember the frequency, it is small f, not f like this, okay, please. Now remember it is moving. If it is moving, sorry, if it is moving towards, the top part will be plus, the bottom part will be negative. What do I mean? I mean we can substitute and say frequency of the listener, it is what we are looking for. Then the velocity, this v, it is the constant speed of 340, speed of sound. Sorry, speed in a, okay, speed of sound in a, yes, plus, why am I saying plus? Because it is moving towards, okay, a, it is moving towards the sound source, so we use plus at the numerator, plus velocity of the listener, which is 10. Then here it's gonna be 340 minus 0 multiplied by 880 hertz. Now we are expecting this answer, the frequency of the listener, to be higher than the frequency of the sound source. Why? Because now if a car is here, okay, if I'm standing and, okay, let me do an example. Uh there is a car, police car. Okay, let me say there is an ambulance, okay, sorry, emitting sound, wee, those sounds, and I am standing here, okay, I'm standing here. When I'm standing here, I can hear, let's say I hear the frequency of 800 and let me do a number of 800 hertz. I'm standing, okay? But as I move, because now I'm curious what's happening there. Why is there an ambulance there? I'm curious. I'm approaching the ambulance to see what's happening. But do you agree with me? When I approach the ambulance, the sound now becomes higher. Okay, so the sound becomes higher now. That we translate into what? Into frequency. No, so it means now the frequency detected now will be higher, the pitch. So it means now the frequency that I detect as I move. Initially, I detected 8. Let's say it emits 800 hertz. When I'm at that distance, I will detect 800. But as I move closer, I will detect, let's say, 1.2 hertz. This does not mean the frequency here changed. No, the frequency did not change, but now the pitch that I hear, or the frequency that I hear as I move closer, is the one that changes. Okay, yes, but of the sound source will never change. Okay, so I get a frequency of 905,88 hertz. Okay, yes, yes. Mm-hmm. All right. Now that's all. Now okay. They say now to us the sketch the sketch below shows the frequency of or frequency recorded by detector A. Okay, this is the frequency of A. Now 6.4 says redraw the graph above for detector A. Oh, redraw the graph above for detector A in your answer book. Okay, I'll assume I've already redrawn that. On the same set of axes, sketch the graph of the frequency detected by detector B. Now I come back here. If this one has a frequency of 905.88, and now can you see this one emitted a frequency to there and the frequency increased? Okay, so this one, when it returns, when this frequency is emitted to B is expected to hear a frequency that is higher than 900 and what? 905.88. Why? Because it is still approaching, moving close, close, close. Why can this is clear? You can see this one emitted 880 hertz. This one detected 905.88. So if A emits the frequency of 905.88 to B. So it means B is expected to hear a frequency that is higher than 905.88. So hence now I say now the frequency of B will be higher. This is the frequency of B. I'm done. For 2 marks. For 2 marks. Parallel. For 2 marks. I'm done. This is you understanding. If it was moving away, it was gonna come at the bottom. Okay, yes. But for this case, this is our 2 marks. So thank you very much for following up with me on question 6. Let's meet again on question 7. Okay. Uh, Charges and as well as actually Coulomb's laws. Okay, thank you.